All right, welcome. We've made it to lecture 4 on our probability review, and we're going to discuss joint density. So, in this lecture, we're going to talk about a density function or a probability distribution for a pair of random variables x and y. And this is, again, this is whenever we're interpreting random variables as measurements from an experiment or from some random outcome. And typically, when we run an experiment, we make more than one measurement. And this is going to apply to any number of random variables that have a joint density function or a joint distribution function. And in here, I just consider two random variables at a time. Everything generalizes to multiple random variables at a time, but I just stick to this just two random variables at a time, as it's easier to picture and includes the most of the theory. Um, Most of the theory just generalizes. So in here, we have two cases for the joint density or the joint distribution for two random variables. For the discrete case, we have this probability distribution. So in the discrete case, we call it probability distribution, and in the continuous case, we have the probability density. And here, the probability distribution in the discrete case is just defined to be the probability function on the two events that x is equal to x and y is equal to y. And this is the induced probability function for two random variables. And you can compute the probability of any event using countable additivity using this probability by using this probability distribution. And similarly, using countable additivity, you can compute the probability of any event by countable additivity and using the density function. And again, I want to keep reminding you that this derivative, it may seem a little bit odd, but this really, you should think that this is equal to the probability that x is in some small interval x plus dx, and that y is in some interval. So it's a small unit of mass, y plus dy. And you divide by dx and dy. And when you think about this probability density function, you can think about it two ways. One is that this is going to be a function that's going to depend on two variables x and y, and it's going to be a positive function, a non-negative function, and it's going to be some type of bump function, and we have to have the condition again that if you sum or integrate over all possible outcomes of x and y, dy dx, then this is going to be equal to 1. This really means that probability of x and y are in R. So that anything could happen. And similar condition exists for probability distribution, and you can think about it this way. Or additionally, you can look at this graph from the bird's eye view, and you can have a contour plot for f of x, kind of think about it this way, where this is the more in the middle, maybe I'll change colors to blue. In the middle, this is the more, the higher, the more likely events. And then as you move away, you have less likely events, and so on. And you have this. So this is going to be our probability density function. And the reason, and for me, I typically like to think about it, the probability density function, I like to think about more about the domain of the random variables x and y. And the reason is because when I'm giving a joint density function, joint probability function, if I want to compute the probability of an event, the way that I set up this computation is through an integral or a summation. And most of the times I think about the continuous case, and the way to set up to compute this probability of this event, that x and y are in E, in the event E, then the way that you do it is that you integrate the probability density function over the region E, of the possible outcomes that are in E. And this is going to be the integral of this probability density function over this region E. So what you want to do is you want to look at your domain, at your possible outcomes for y, possible values of y and x, and you want to integrate over that region. And this is how you compute the probability of a specific event for two random variables. And in the discrete case, you do the same, and you just have to figure out which outcomes you want to include in the summation. So let's look at some examples. One typical example is the sum of two random variables. Let's switch back to sum of two random variables. So in here, we have our two random variables x and y, and we have a joint density, which is going to be the probability function xy, or the density function of x and y. And what we want to compute is the probability that x plus y is equal to c. Some number c, some real number. And this is really equal to the probability that the pair xy is in the event E. And here maybe we want to denote it E sub c to explicitly show the dependence on z, where E of z is the event of x and y such that x plus y is equal to c. So this is going to be, when we write the probability that x plus y equals to c, this event is the same as this event, where x and y are picked so that their sum is equal to c. And I can actually rewrite this event, represented a different way, by this collection of tuples, which is k comma z minus k, such that k is in the integers or in R, depending whether you're in discrete or continuous case. And pictorially, this is the way that it looks if you're in the domain of the random variables x and y. E sub c is the probability that x plus y equals c, is that the random variables lie on this straight line. So that the x plus y are equal to c, and the way that we can parameterize it is by parameterizing it with one variable k, and for each k you're going to have this tuple that's going to lie on the line E sub c. So to compute this probability, again, we want to take the integral or the summation of the probability density of the probability distribution over the domain for the pair of random variables, the domain of the event. And here, this is a line. And so this is what I've done here. This is going to be a summation, and this is going to be the summation over this line. For the continuous case, it's an integral over the real line, where k is going to parameterize the point along this line. And it's going to be a summation, and we have this. And in here, for this, should actually be a k. And in here, we have the same summation in the discrete case, and we have parameterized this line using a number k, and it's just a sum over this region. And in here, this is going to be our probability formula, or this is going to determine the probability of the sum of two random variables, this formula right here. So this is a application of the joint probability density, a common use of it to compute this type of probabilities when you have multiple random variables. Now let's look at a different example. Now, a more precise example where we actually take two Bernoulli random variables. So we have that xi is going to have distribution Bernoulli p. So we have x1 and x2, and we define the joint probability density to be just the product of this probability distribution, the joint probability distribution to be the product of this probability distributions. And here pi is just the Bernoulli distribution, as noted here. So which is going to be p when xi is equal to 1 and 1 minus p otherwise, or actually it shouldn't be otherwise. This should be xi is equal to 0 and then 0 otherwise. So we have these two random variables, and what we want to compute is now the distribution of this. And we use the same formula as in the previous slide. In the event that this is going to be the probability that x1 plus x2 is equal to x. So this is the distribution function for x1 plus x2. So this is probability that x1 is equal to x2. And then if you do the formula, this is the formula that you want, that the events such that x1 plus x2 are equal to x. And it turns out now for x1 and x2, each of the random variables can take the values 0 or 1. But when you consider the sum of x1 and x2, the values that x1 plus x2 can take are going to be 0, 1, or 2. And this is, you can interpret x1 plus x2 as the number of heads in two coin flips. And as we saw before, you can show that this is going to be the binomial distribution. This is equal to the binomial distribution with n is equal to 2 and p is equal to p. And the way that I've done this computation is that here, this event, that x1 plus x2 equals to x, is equal to 2 choose x. So this is the number of ways to choose x from 2, the number of ways to choose x heads from 2 coin flips. And additionally, the second observation is that for each element here in this event, each x1 and x2, which add up to x, for each pair of this, the probability of this event is going to be p to the x times 1 minus p to the 2 minus x. And this is for each x1 and x2 in this event. And so that means that all these events have the same weight, and we just need to count the possible ways to get x1 plus x2 equals x. And this is going to be 2 choose x. So this is another sample computation for the sum of two random variables. Again, here we already discussed this in a previous lecture, that the sum of Bernoulli random variables is going to give you a binomial distribution, and in particular, due to the interpretations that we have, that xi's are coin flips, and the Bernoulli distribution is the total number of heads and coin flips. This should be true, that this result that x1 plus x2 is going to have the binomial distribution. So from just the interpretation point of view, then we should already kind of guess this solution, but here we're doing it explicitly just to see how the computations work and see that everything's consistent or everything's meeting our intuition. So let's continue with more examples. The next one is what we call a marginal distribution. So given our two random variables with a joint distribution Pxy or a joint intensity Fxy, we define a marginal distribution. And here, what's happening really is that if we have a joint distribution or density, we could, this really means that we're running an experiment and measuring two variables x and y, and then looking at the probability function for these two random variables. But we can just forget about y. We might not be interested in the additional data or the additional measurement we take. And we need a method or a precise way to just forget about the additional data from y. And this is what the marginal distribution is. It's just forgetting about the second random variable. And we define it in abusing notation. I just define it as p sub x, as if y didn't exist. And this is just probability of x equals x. And I don't care about y, I just care about this event. And in particular, this is going to be this summation for the joint density. So I'm just going to sum over all possible values of y, the joint density for x, y. And here x is fixed, and y is summed over all possible values of y. And here, this event x equals x corresponds to the event, this event, that x equals x is all pairs xy such that y is any r, or c, really, or depending on the continuous or discrete case. And again, this is the general recipe to computing the probability of certain events using a joint probability density. You figure out the event, and I draw it on the domain for the possible values of x and y, and then I sum over that region that corresponds to E. So in here, the region is that you fix x, and E is going to be this event, this vertical line, and this is what we do. And in here, this is going to be the summation in the discrete case. And in the continuous case, again, you have that it's going to be a probability density, and I'm abusing notation for the one that's equal to, or that is identical to the probability distribution and density for one random variable, because it is the probability density for one random variable. Then in here, but using the joint density, I can compute this probability, this density function, using the general recipe of integrating over the event E. And here the event is this, and we sum over this region, which that means that x is fixed, and we're summing over all y, because we don't care about the value y. We're forgetting about this value y, so we just add all these possible values of y. And this is going to be the probability. They're going to each contribute to a probability of x equals x. And this is an important idea or an important object that appears, because oftentimes you're going to be given the joint probability density function or the joint probability distribution, and you just want to extract less information. And the way that you do it is through this summation. Now, I'm going to wrap up this lecture with the proof of linearity. And for this proof of linearity, we really needed to have this joint density function, and I'm proving it for the continuous case. The discrete case works similarly. So let's just go step by step. And again, linearity, what I really want to show here before we get into it, and I'll remind you, and this is from the previous lecture, is that expected value of x plus y is equal to expected value of x plus expected value of y. So I'm just gonna start from the very big definition of this expected value. I have that the expected value of this is going to be, if I say, for instance, that the expected value of this is going to be this weighted average. So I look at the density function for x plus y, thinking of it as one random variable, this density function, and for each outcome I weigh it by its probability density. And from one of the earlier examples, we know that the formula for the density function for the sum of two random variables is given by this formula using the joint density function. So I sum over all the outcomes where the summation is equal to z. So if I take x plus y is going to equal to z, and there's going to be this graph, and this is the graph that we saw earlier, and I'm taking a sum over all this, and k is going to be the variable parameterizing this line e for all the pairs x and y that add up to z. So now we have written things in terms of the joint density function, and in here I'm gonna do a u substitution to go from this line to this line, and really what I'm doing is gonna be u is equal to z minus k. And once I do, and actually additionally note that the domains of integration are both the whole real line. So, and since the whole real line is the domain of integration, when I do this change of variables or this u substitution, I still have that the domain of integration is R2. But I've changed this z into k plus u. And now I have this joint density function. So this is just u substitution. And now I'm going to distribute the k and the u and just switch the order of integration, du, dk, dk, du. And I'm going to distribute, and so this is just a manipulation of the integral. And then I have this integral plus this integral. And I've switched the order of integration in the two different ones. And in particular, in this one, I've done this order integration so I can do this integral first with respect to du, where we don't have any k dependence. And you can recognize this from the previous example that this term in the parentheses is going to be the marginal distribution of x. Because in here, I'm summing over all u, and I keep k fixed, and this is going to give me this marginal distribution. Similarly, for this term over here, I keep u fixed, and I sum over all k's. So this is dk, so this is going to be the marginal distribution with respect to y. So I'm going to have fy and fx, and now to end the proof, I have that this is the definition of the expected value of x. So it's the weighted average. So the outcome is k, and I weighted against the probability of the outcome k, and this is with the marginal distribution of x. And similar, and this is going to give me this term. And here I do a weighted average again. So the outcome is u, and I have the weight given by the probability density of y. So I get this expected value of y. So here we've come from the beginning that this expected value of x plus y is going to be equal to the expected value of x plus expected value of y. And that's it for this lecture. This is just this is just a lecture on how to use the joint probability density. And from the joint probability density, you can compute the density of the density for marginal distributions, or for sum of random variables, or compute probability for events involving more than one random variable. And we'll see that additionally you can use it to compute conditional probabilities, and we'll discuss that in the next lecture, lecture 5. And that's it for now. Thanks for tuning in.